In this video, we'll talk about the squeeze theorem, which is a topic in calculus that many students struggle to understand. With the squeeze theorem, your goal is to evaluate the limit as x goes to a of f of x. So the goal is what is happening with this blue wavy thing as x goes to a. Oftentimes, we use the squeeze theorem when it's too hard to actually know what's happening with f directly. So what we do is find two functions g and h such that one of the functions, in the picture I've drawn g, is above the function f, and the other function in the picture I've drawn, that's h, is below. So we'll write this in symbols. So h is below f of x, which is below g of x. And these h and g functions that bracket the function f need to have another characteristic, which is that their limits at a are the same. You can sort of think of this as they meet at x equals a. We have the function f, that's the blue wavy thing. It's too hard for us to work with. So we have to build two functions g and h that bracket f, and they go to the same place at x equals a. They squeeze f. If you live in an urban environment in the United States, this is sort of like when you're on the highway or the freeway and they close down a bunch of the lanes for construction and they squeeze you in to like one line of cars on the shoulder. It's sort of that feeling. You're all getting squeezed into this one spot. Okay, so the example we will work is using the squeeze theorem to show that the limit as x goes to 0 of x squared times sine of 1 over x equals 0. I have graphed it here on the side to give you the flavor that does feel like it's coming in toward the origin here. So from the graph, it's not entirely unbelievable that the result should be 0. But now we're going to have to find functions g and h that bracket the function f. So this is our function f here, so that their limits also go to 0. Now, why is this function f so unruly? Well, if we tried to plug in x equals 0 into here, we get the sine of 1 over 0, which is a what? We don't know what that is, call it undefined. So even in the limit it's undefined, there's too much wobbling, so we can't get a handle on that part. So what we're going to do is start with something we do know, which is that -1 is less than or equal to sine of anything which is less than or equal to 1. So this is a trigonometry fact. Why we're conjuring this trigonometry fact up is going to be revealed in a few moments, but big picture, we're trying to get control of this wobbly thing, sine of 1 over x. And at the outset, the only thing we really know is that trig functions sine and cosine are both locked between -1 and 1. So it's not a big stretch to think that we might start there as a means of bookending this wobbly thing that's out of our control. What's not clear is that is actually going to work. How do we know that we don't need something better? With most squeeze theorem exercises at the introductory level, this is sort of where they start. You have some trig function that's wobbling around like crazy, and you start by getting it locked in between two values. In the end, we want the middle of this inequality. We want this part to look like this. And if we compare the two right now, what it's missing is an x squared. So I'll just multiply the middle by x squared. And then the price I have to pay for multiplying the middle by x squared is I now have to multiply all of the parts of the compound inequality by x squared. Now this is legal because x squared is positive. Now there are squeeze theorem exercises where you try this and it's not exactly legal because the thing you're multiplying by might be negative, and so now you have to go down some logical sort of rabbit hole type things to navigate your way out of the forest. But this one, x squared is positive, it's totally legal. We simplify. On the left side we have -x squared. It's less than or equal to x squared times sine of 1 over x. It's less than or equal to x squared. We just check out what is the limit. As x goes to 0, now that's our original limit as x goes to 0, negative x squared goes to negative 0 squared, which is 0, and x squared goes to 0 squared, which is 0. And so the result is 0 is less than or equal to the limit as x goes to 0 of the function that was out of our control, and that is also less than or equal to 0. So these purple arrows, this step here is taking the limit of all sides. I mean, there's 3 parts of the compound inequality, let's call them sides. So the limit as x goes to 0 of the negative x squared is 0, that's over here, and the limit as x goes to 0 of the positive x squared is also 0. That's how we get these zeros at the bookends, and then we apply the limit in the middle, and we get what we started with. Now, when we look at this compound inequality, we have some object that is locked between 0 and 0. The only number that can be locked between 0 and 0 must be 0, and that's the essence of the squeeze theorem. Now, this example of applying the squeeze theorem is a little bit trickier. I have the limit as x goes to 0 of x times sine of 1 over x, and I'm trying to show that that equals 0. I have the graph of that unruly function on the left here, and we can see that the graph strongly suggests that, in fact, we do arrive at the origin. The question is trying to sort out the g and h bracketing functions for this function f of x. So this is our function f, and we're looking for a g and an h. Now this graph is pretty helpful because it sort of suggests to us to maybe use these two v's as our bracketing functions. And the reason these v's are helpful is because they are sort of famous. They're the absolute values. So this is absolute value of x up here, and this is the negative absolute value of x down here. Question is this statement true? Because if we can show that the statement is true, then we are done. As we did in the previous example, we'll start with pretty much the only thing we know about this ridiculously out of control wavy function. It's locked between negative 1 and 1. We want the middle to look like our function f, so we'll just introduce an x times to make it look like f. But we have to pay a price. Here we have to multiply everything by x. This, however, is not always legal. This is only true if x is positive. And now we get negative x is less than or equal to x. Sine of 1 over x is less than or equal to x. Again, if x is positive. Now let's consider the case, well, what if x was negative? What would happen in that situation? So we'll do that over here. We'll start with the thing we know, which is the sine wobbly function thing is locked between negative 1 and 1. We'll multiply the middle by x to make it look like our target function f. But now we have to multiply everything by x. But now, if x is negative, the inequality directions have to change. So now these are pointing this way. And we simplify. So negative x is greater than or equal to x. Sine of 1 over x is greater than or equal to x. Now we have to recall an old algebra fact. This is the really tricky part for most students on this example. Absolute value of x. What most students remember about absolute value of x is if x is positive, the absolute value function does nothing. But if x is negative, they remember the absolute value is turning it positive. Now, the tricky thing here is to realize that putting this negative in front of the x is turning it positive if x is negative. So let's just try some numbers. If x is -3, then negative x, which is -3, is +3. Maybe x equals -6. So then this will be -6, which is +6. So we can see that that negative is indeed flipping it positive. So now this allows us to replace this negative x over here in this condition of x being negative with an absolute value of x. Now, what I can do is this trick. Here I can replace this x here with a negative x, and then I can replace this negative x with an absolute value of x, as we did on the left side over here. And so that leaves this negative here in front of the absolute value. So over here I get negative absolute value of x. Now, in the case where x is positive, x is the same as absolute value. So over here on this one, that was easier for us to work with. We get x just replaced by absolute value of x. Now, one question is, why aren't we changing that x with an absolute value? The answer is because our target does not have an absolute value in it. On the left side, we're just going to replace that x with an absolute value, leaving the negative outside of it. And now we combine these two lines. They're actually the same thing, just written in reverse. And the one on the left covers the case where x is negative, and the one on the right covers the case where x is positive, but because they're identical, this is true for all x not equal to 0. Now we have our bookended functions. We have this thing we were wondering about that was suggested by the graph. So the bookends are created, our g and h are created. Now we're wondering what happens when we apply the limit to all three sides. So this is as x goes to 0. Well, the absolute value of 0 is 0. So this goes to 0, and this goes to 0. And so this gives us that 0 is less than or equal to the limit as x goes to 0 of x sine of 1 over x, which is less than or equal to 0. And again, we have our object is between 0 and 0, and the only possible number that could be between 0 and 0 is the number 0. And so therefore, we have the desired result, the limit as x goes to 0 of x sine of 1 over x is 0, as we set out to prove.